For 9 years, the most important fossil in Colombia sat in a display case labeled Petrified Branch. Nobody could find the key to the cabinet. A scientist had to photograph it through the glass. It wasn't a branch, it was part of a snake weighing over a ton, and the reason it got that big should worry you. The story starts with a man named Henry Garcia, a Colombian geologist working at Querrellón, one of the largest open-pit coal mines on Earth, out in the desert of La Guajira near the Venezuelan border. Sometime in the 1990s, he picked up something odd. He didn't know what it was. He put it in the coal company's display case. Somebody wrote Petrified Branch on the label, and everyone forgot about it. 9 years passed. Then in the early 2000s, an undergraduate geology student named Fabiani Herrera came to Cerrejón on a field trip. He was walking around the coal fields, picked up a piece of sandstone, and turned it over. There was a fossil leaf pressed into it. He picked up another rock, same thing, and another. That kept happening, and it was strange enough that Herrera showed the rocks to a geologist named Carlos Jaramillo, who was working for the state oil company at the time. Jaramillo looked at them and thought Cerrejón might be worth a proper look. In 2003, they organized a real expedition and invited Scott Wing, a fossil plant curator at the Smithsonian. When Wing got to the mine, he wandered past the coal company's display case and stopped at the thing labeled Petrified Branch. It wasn't a branch. He asked if someone could open the cabinet. Nobody could find the key. So Wing did the only thing available to him. He took out a point-and-shoot camera and photographed it through the glass, went home to the United States, and emailed the pictures to Jonathan Block at the University of Florida. Block's reaction, in his own words, was that he flipped out. What he was looking at through a pane of glass, in a blurry photo, in a coal company lobby, was part of the fossil jawbone of a land animal. And terrestrial vertebrates of that age had essentially never been found in the tropics of South America. Not because they didn't exist, but because nobody had ever found the rocks. So they went back. What came out of that mine over the next decade is one of the strangest fossil sites on the planet. The Cerrejón Formation dates to roughly 58 to 60 million years ago, a few million years after the asteroid in the middle of the Paleocene. And it turned out to be the earliest record of a neotropical rainforest anyone has ever found, the beginning of the ecosystem that would eventually become the Amazon. That in itself is a big deal, and it's worth understanding why. Rainforests are terrible at making fossils. Everything rots. The soil is acidic, the biology is aggressive, and organic material gets recycled fast instead of getting buried and preserved. So the fossil record of tropical forests is close to empty, which means the origin of the most biodiverse ecosystem on the planet was more or less a blank. Cerrejón filled part of that blank because coal swamps preserve plants. And what the plant fossils showed was that the modern rainforest, the family structure of it, the dominance of certain flowering plant groups, the big smooth-edged leaves, was already assembling itself within a few million years of the extinction that killed the dinosaurs. The plants alone are remarkable. Fossil leaves from the ancestors of beans, bananas, and cacao. The chocolate plant, growing in Colombia 58 million years ago in a forest that has no other record anywhere. But it was the animals that got weird. They pulled out a turtle called Carbonemys, the coal turtle, with a shell around 1.5 meters across. They found dinosaurs, crocodile relatives that had survived the extinction independently of modern crocodilians, including one called Acherontosuchus that ran about 6 meters, comparable to the biggest saltwater crocodiles alive today. Then a second dinosaur species, then a third, a small one, only about 2 meters long. Everything at this site was enormous, and the ones that were not enormous were prey, and mixed in with all of it were vertebrae that the team initially cataloged as crocodile. That mislabeling lasted through the entire expedition, right up until the fossils reached the Florida Museum of Natural History and somebody actually compared them properly. They were not crocodile vertebrae. They were snake vertebrae. And you can tell because snake vertebrae have a very specific arrangement of ridges and holes and processes that identify not just the animal, but the family. These belong to Boidae, the boas. The problem was the size. Snake vertebrae scale predictably with body length, which is why they are so useful. A boa's backbone tells you how long the boa was. Run these numbers, and you get a snake somewhere just under 13 meters long, weighing roughly 1,135 kilograms. Over a ton. Longer than the largest T-Rex. Eventually, the site produced something like 186 fossils representing around 30 individual animals of this one species. It was not a fluke specimen. There was a population of them. In 2009, the team published, led by Jason Head, and named it Titanoboa cerrigonensis. There is one more piece to the discovery, and it came years later. For a long time, all anyone had was backbone. No skull, which is a problem because vertebrae tell you how long an animal was, but they tell you almost nothing about how it lived. A skull tells you what it ate. Then field teams went back to Cerrigon and found skull material, pieces of the upper and lower jaw, the palate, the brain case. Reconstructed, the head measured around 16 inches, implying a body length at the upper end of the estimates. The skull said something nobody expected. In most snakes, the teeth are firmly fused to the jaw by a bone-like tissue. Titanoboa's teeth were only weakly attached. It also had a lot of them, more and smaller than you would expect for a boa of any size. Add a shallow quadrate angle and reduced articulation between certain skull bones, and you have a specific anatomical signature. That signature belongs to fish eaters. You see it in modern snakes like the brown water snake and the banded sea crate. Thin, numerous, loosely set teeth are for gripping something slippery that is trying to escape, not for holding a struggling mammal. Which means the largest snake that ever lived was, as far as we can tell, primarily eating fish. Big ones. The rivers at Cerrigon were full of lungfish and osteoglossomorphs, some of them enormous. And there was a small dinosaur at the site called Cerrigonisuchus, only about 2 meters, which researchers think was probably on the menu too. No modern boa specializes in fish. Titanoboa is the only one we know of, living or extinct. So the picture that forms is not the one on the movie poster. Not a land monster crushing mammals. A semi-aquatic ambush predator lying in warm swamp water with most of its bulk supported by buoyancy, waiting for something to swim past. That buoyancy detail matters more than it sounds. On land, a ton of snake is a problem. Every movement means dragging that mass across the ground, and the animal's own weight presses down on its organs and lungs. In water, the weight effectively disappears. The swamp was not just a hunting ground for Titanoboa. It was structural support. This animal probably could not have existed as a purely terrestrial creature at that size. We also have some sense of how long they lived, from growth marks preserved in the bone. Snakes lay down annual layers a bit like tree rings, and the analysis on Titanoboa suggests individuals may have lived 60 years or more, though the researchers themselves flagged uncertainty in that reading. 60 years is a long time to keep growing, and large snakes never really stop. Which means the 13-meter estimate probably isn't the ceiling. It's just the biggest one that happened to die somewhere its bones could turn to stone. So that's the discovery. A giant snake found by accident in a coal mine after 9 years in a display case labeled as a branch. But the discovery isn't the interesting part. The interesting part is the question it forced, which is the one this whole video is actually about. Why was everything at Cerrigon so big? Not just the snake. The turtles were oversized. The crocodile relatives were oversized. You've got an entire ecosystem where the reptiles are running consistently larger than their modern equivalents, in the same latitude, in the same kind of environment. That's not random. Something about that world was letting cold-blooded animals get bigger than they can get now. The answer turns out to be a piece of biology simple enough to explain in 2 minutes, and it led to a claim so provocative that other scientists published rebuttals in Nature trying to tear it down. We'll get to that fight. First, you need the rule they were fighting about. Reptiles are Poikilotherm S. Cold-blooded in the everyday phrase, though that's slightly misleading. It doesn't mean their blood is cold. It means they don't generate their own body heat internally the way you and I do. Their body temperature tracks the temperature of the environment around them. Now, metabolism isn't just how fast you burn calories. It's every chemical reaction keeping the animal running, digestion, tissue repair, growth, all of it. And chemical reactions run faster when they were warmer. That's basic chemistry, and it applies to a snake exactly the way it applies to anything else. So a reptile in a warm environment has a faster metabolism. It digests faster, grows faster, and can sustain more body mass. A reptile in a cool environment has all of that dialed down, which sets up a ceiling. There's a maximum size a cold-blooded animal can reach in a given climate, because past a certain point, it can't run enough metabolism to keep that much body alive. There's a second half to this that makes the ceiling even more interesting, which is that being cold-blooded is what makes enormous size affordable in the first place. Compare Titanoboa to a mammal of similar weight. A ton of warm-blooded animal, a bison, a giraffe, has to eat constantly because it's burning fuel every second just to hold its temperature steady. That's an enormous, relentless energy bill. A snake doesn't pay it. A large constrictor's metabolism is a fraction of a comparable mammal's, and after a big meal, it can go months without eating again. So a cold-blooded animal can carry far more body mass on far less food than a warm-blooded one can. Which means heat isn't just permission to grow. It's the entire economic model. Let the environment run your metabolism instead of your dinner, and you can afford a body no mammal predator could ever fuel. That's the trade, and it's a good one, right up until the environment stops holding up its end. In 2005, a group of researchers led by Anastasia Makarieva quantified this across living animals, and the pattern they found was startlingly clean. Compare the largest Poikilotherm species from tropical, temperate, and polar climates, and the maximum body length drops by a factor of 2 to 3 for every 10 degrees Celsius of cooling. 10 degrees, 2 to 3 times smaller. Now flip it around, because this is the move that made Titanoboa famous. If the maximum size of a cold-blooded animal is set by the temperature of its environment, then the size of a fossil cold-blooded animal tells you the temperature of an environment that no longer exists. Head and his colleagues took Titanoboa's estimated length and mass, ran it through that relationship, and produced a number for the mean annual temperature of Paleocene Colombia. They gave the method a name that I love because it sounds completely made up: paleophytothermometry. Snake thermometry. You've got a thermometer that's been dead for 58 million years, and the reading is written in the width of its backbone. The number they got was 30 to 34 degrees Celsius as a mean annual temperature. To put that in context, Cartagena on the Colombian coast today averages somewhere around 28. A modern tropical rainforest sits below that. Head's estimate put the Paleocene tropics roughly 3 to 5 degrees hotter than anything comparable today. Sustained as an annual average, not a heat wave, not a bad summer, just the ordinary temperature of the world. 3 to 5 degrees doesn't sound like much until you attach it to a year-round average. The difference between a rainforest and a scrubland is a few degrees. The difference between an ice age and the present is about 5. Averages are where climate lives. The extremes are just weather. This is where it stopped being a paleontology story and became a climate story, because that number landed in the middle of an argument that had been running for decades. Here's the background. During Earth's greenhouse phases, periods with no polar ice caps at all, with forests growing at high latitudes, the obvious question is, what was happening at the equator? For a long time, the prevailing idea was something called the equable climate hypothesis, that the poles warmed dramatically. The temperature gradient between pole and equator flattened out, but the tropics themselves stayed roughly where they are now. There was thought to be some kind of thermostat, some upper limit that kept the equator from cooking. That mattered because it implied a kind of built-in safety valve. If the tropics have a ceiling, then no matter how much you warm the planet, the hottest inhabited regions stay livable. Titanoboa said no. Titanoboa said the tropics got hotter too. A snake found in a coal mine was suddenly a data point in a debate about how the climate system behaves when you push it, which is not a purely academic question given where we are currently pushing it. So the paper hit hard, and then the field hit back. This is the part almost nobody tells you about Titanoboa, and it's my favorite part of the story. Within months, Nature published 2 separate technical objections to the snake thermometer, both arguing that the method doesn't work. The first came from Mark Denny and colleagues, and the argument is beautifully counterintuitive. Their point was about heat production. An animal that big generates a lot of metabolic heat internally, and it has a low surface area to volume ratio, which means it's bad at shedding heat to its surroundings. Run the numbers, they argued, and a 1,135 kilogram snake living in a 30 to 34 degree environment wouldn't have thrived. It would have overheated. It would have cooked itself from the inside. Think about what that means for a second. It's the same problem an elephant has, and why elephants have those enormous ears full of blood vessels. At a certain body size, getting rid of heat becomes harder than generating it. Denny's argument was that Titanoboa had crossed that threshold, and that the hotter you make its world, the worse its problem gets, which flips the whole conclusion. If Denny is right, Titanoboa's size doesn't prove the world was hotter. It might actually prove the world was cooler than had estimated, because that's the only way an animal that large could dump enough heat to survive. The second objection came from James Snyderman and made a different point about behavior. A snake weighing over a ton has enormous thermal inertia. It heats up slowly and cools down slowly, and that gives it options. It can move into water. It can move into shade. It can bask when it needs to and hide when it doesn't. Snyderman's argument was that because Titanoboa could regulate its own temperature behaviorally, its body size reflects the temperatures it chose to occupy, not the average temperature of the region, which makes it a bad thermometer, because a thermometer that can walk away from the heat isn't measuring the room. Note how well that objection fits the fish-eating skull. If this animal spent most of its life half submerged in swamp water, and the anatomy says it probably did, then it was living in the most thermally stable environment available. Water buffers temperature. A snake in a river is not experiencing the air temperature of Paleocene Colombia. It's experiencing the water temperature of a specific swamp, which is a different number. Head and his team published a reply defending the method, and the argument has never fully settled. Other challenges piled on. A 2023 study compared Titanoboa's growth rate to modern anacondas and found it only slightly faster, which doesn't strongly support a heat-driven size boost. And when you apply the same equations to Megalania, the giant extinct monitor lizard from Australia, the numbers come out badly off from what the fossils actually show. A method that gets a known case wrong is a method to be careful with. So the honest position in 2026 is that the snake thermometer is contested. Some paleoclimatologists think it's a genuinely useful proxy. Others think it's a clever idea that doesn't survive contact with the physics of large-bodied animals. But, and this matters, the underlying picture held up. Because Titanoboa was never the only evidence. Independent methods were pointed at the same question: carbon isotope ratios measured in the fossil leaves from the same formation, marine core samples, pollen records. Those approaches don't care how big any snake was, and they came back with temperatures above 25 degrees and possibly as high as 31 degrees. So the specific number is disputed. The overall conclusion isn't. That Paleocene rainforest was hotter than any rainforest on Earth today, and the animals living in it were correspondingly larger, which raises the obvious follow-up. If heat really does set the ceiling on how big a cold-blooded animal can get, then this shouldn't be a one-time event. It should have happened again, somewhere else, whenever the planet got hot enough. In 2024, that's exactly what turned up, in India. under conditions so similar it's almost funny. The fossils came out of the Panandro lignite mine in the Kutch district of Gujarat, another coal mine on another continent. They'd been excavated back in 2005, and in a detail that should sound familiar by now, they were labeled as crocodile and shelved. They sat in a drawer at the Indian Institute of Technology, Roorkee, for 19 years. Then a postdoctoral researcher named Debajit Datta, working with Sunil Bajpai, pulled them out and actually measured them. 27 vertebrae, some still articulated, some up to about 11 centimeters across. Broad, thick-walled, cylindrical, the backbone of something enormous. The shape told them something beyond size. Those proportions, broad, heavy-walled, cylindrical rather than streamlined, point to a thick, muscular, slow-moving body, not a sleek swimmer. The researchers interpreted Vasuki as a slow terrestrial ambush predator, something like the largest living pythons scaled up past the point of plausibility. An animal that didn't chase anything. It found a place to lie still and waited, which is a different life from Titanoboas. One was a semi-aquatic fish specialist. The other was a heavy ground-based ambusher. Different families, different continents, different hunting strategies, different diets, and both arrived at roughly the same impossible size. They named it Vasuki indicus, after the serpent king who coils around Shiva's neck in Hindu mythology. It dates to roughly 47 million years ago, the Middle Eocene. Depending on which measurement landmark you use in the size equations, and the two standard methods disagree by about 4 meters, which is worth knowing, the length estimate runs from about 11 meters up to 15. At the high end, that's longer than Titanoboa. I know that comparison is the one everyone wants to make, and it's fine, but I'd argue it's the least interesting thing about this animal, because here's what actually matters. Datta and Bajpai ran the same calculation Head did. Same logic, same relationship between poikilotherm body size and temperature. And they estimated a mean annual temperature of roughly 28 degrees Celsius for Eocene Kutch. The world Vasuki lived in was, if anything, stranger than Titanoboa's. Kutch today is arid scrubland, hot, dry, sparse. 47 million years ago, it was a coastal lowland on the edge of a shrinking sea, choked with swamp forest and tidal marsh. The rocks Vasuki came from sit right at a hyperthermal event, one of the sharp global temperature spikes that punctuate the early Eocene, in a period that was already a greenhouse world. India itself was somewhere strange at the time. It had broken off the southern supercontinent and was drifting north as an island, isolated, carrying its own private evolutionary experiment. The swamp Vasuki hunted in also contained catfish, turtles, crocodilians, and at the coastline, some of the earliest whales. Small, semi-aquatic ones that hadn't fully committed to the ocean yet, which is worth pausing on. A giant snake and the first whales sharing a coastline. Both of them enormous experiments happening in the same hot, wet corner of a drifting island. One of them, the end of a lineage. The other, the beginning of one. So that's twice. 2 giant snakes, 2 continents, 2 epochs, each one showing up in a hothouse. Now here's the part that turns a coincidence into a pattern. Titanoboa was a boid. Same family as modern boas and anacondas, with the flexible skull and wide gape feeding that defines advanced snakes. Vasuki was not. Vasuki belonged to the Matsuidae, an ancient family with no living members at all. Nothing alive today carries their blueprint. Their skulls were low and rigid. They never evolved the flexible jaw. They are so distantly related to boas that scientists still argue about whether they sit inside the group containing living snakes or outside it entirely. 2 lineages that had been separate for tens of millions of years, that fed differently and were built differently, both produced giants of roughly the same scale in different parts of the world whenever the planet ran hot. That's the argument. Not that one snake got big, that the same ceiling lifted twice independently for 2 unrelated animals in 2 greenhouse periods. If gigantism were mostly about genetics, some special lineage that happened to have the capacity, you wouldn't expect that. You'd expect it once in one family, Getting it twice in unrelated groups in hot intervals points at the environment rather than the animal. There's a third data point too, and it's older. Before Titanoboa was described, the record holder was Gigantophis garstini from Eocene Egypt, around 10 meters, described all the way back in 1901, and it held the title for more than a century. Gigantophis was also a matsoid, like Vasuki. Same family, different continent, and it lived during the late Eocene, in the tail end of the same greenhouse world. So the pattern isn't two, it's at least three, spread across South America, Africa, and Asia in two separate families, all clustered in the hottest stretch of the last 66 million years. And then they stop. There is no giant snake from the Oligocene, or the Miocene, or the Pleistocene. Nothing since has come close. The largest snake alive today, the green anaconda, tops out around 7 meters and maybe 200 kilograms, roughly half the length and a fifth of the mass of Titanoboa. That gap isn't because snakes forgot how. It's because the world cooled and never went back. The method has kept traveling too. Had applied the same size temperature logic to a giant lizard from Myanmar called Barbaterex, nicknamed after Jim Morrison, because the describing team went with the Lizard King. A 2024 study used the approach on a Miocene snake from Palasava in India. What started as an argument about one Colombian fossil turned into a general technique for reading ancient temperature out of cold-blooded body size. Which brings us to the ending, and the ending is the same for both snakes. The world cooled. Titanoboa lived a few million years before the Paleocene-Eocene thermal maximum, an event around 56 million years ago when atmospheric carbon spiked and global temperatures jumped another 5 to 8 degrees for roughly 200,000 years. That event is worth sitting with because it's the closest analog we have to what's happening now. A massive release of carbon into the atmosphere, global temperatures climbing fast, oceans acidifying, ecosystems reorganizing. The main difference is speed. The PETM played out over thousands of years, and we are doing it in a couple of centuries. For Titanoboa, that spike should have been a golden age. More heat, higher ceiling, bigger snakes. But after it, the long slide began. Around 49 million years ago, the climate started cooling in earnest, and it kept going, eventually building the Antarctic ice sheet and much later, the world we live in now. We don't know precisely when or why Titanoboa disappeared. What we can say is that a snake of that size needed an average temperature somewhere around 30 or 31 degrees to sustain itself, and the world stopped providing it. Notice there's no drama in that ending. No competitor, no catastrophe, no asteroid. The temperature went down a few degrees over a few million years, and a 13-meter snake stopped being something the planet could support. Vasuki's story runs the same way later. The Eocene greenhouse ended, temperatures fell, the tropics contracted, and the giant matsoids went with them, gone from India, gone from Africa, gone from South America. That entire family, which had been producing giants for tens of millions of years, faded out almost everywhere the climate tightened. Same ceiling, lowering, same result. There's something almost mundane about that, and I think it's the most striking thing in this whole story. These were the largest snakes that have ever existed. Neither was killed by a rival or a predator or a catastrophe. The thermostat moved a few degrees, and the animals that had been built by heat simply couldn't be built anymore. So, what does this mean for us? Because I know where that question goes, and I want to be honest about it rather than dramatic. The planet is warming. And yes, the relationship between temperature and poikilotherm body size is real and measurable. You can find modern examples of reptiles growing larger at the warm end of their range. But no, we are not getting Titanoboa back. A 13-meter snake needs more than heat. It needs a stable hothouse sustained across millions of years, not decades. It needs enormous continuous wetland, uninterrupted by roads and farms and cities. It needs prey at a density that doesn't exist anymore. And it needs the time. Titanoboa may have lived 60 years or more as an individual, and the lineage had millions of years of runway to get that big. The warming we're driving is happening on a time scale where evolution mostly can't respond at all. Species don't grow. They move, or they shrink, or they die. What these snakes actually tell us is something more useful and less cinematic. They tell us that the size and shape of life on this planet is set by conditions we don't control and mostly don't notice. Titanoboa wasn't a monster. It was a completely ordinary animal, an ambush predator eating fish in a swamp that happened to live in a world with the thermostat turned up, and it grew to exactly the size that world allowed. When the setting changed, it wasn't that Titanoboa failed. It was that the animal stopped being possible. That's the part I keep coming back to, because it inverts how we usually think about extinction. We tend to imagine it as a defeat. Something outcompetes you. Something eats you. Something kills you. But the largest snakes that have ever existed weren't defeated by anything. The conditions that made them simply stopped, and they went with them. They were never separate from their climate. They were an expression of it, which is also why the whole "will global warming bring back giant snakes" question misses the point, even though it's the first place everyone's mind goes. The interesting thing isn't that heat makes big reptiles. It's that a fossil backbone in a Colombian coal mine and another one in an Indian drawer are both readable records of what the atmosphere was doing tens of millions of years before anyone was around to measure it. Two snakes on two continents, tens of millions of years apart, from families so distantly related they barely count as cousins, tell the same story, that what exists depends entirely on what the climate permits. There's one more thing worth saying about Cerrejon, and it's the detail I find hardest to shake. That fossil sat in a display case for 9 years, labeled as a branch. The vertebrae were cataloged as crocodile through an entire excavation. Vasuki's bones sat in a drawer at an Indian institute for 19 years, also labeled as crocodile. The evidence was already collected. It was already sitting in cabinets. Nobody had looked properly, which makes you wonder what else is in a drawer somewhere, mislabeled, waiting for a student on a field trip to pick up the wrong rock and turn it over. We're the first species that gets to move the dial on purpose. We just don't get to choose what comes out the other side.